Yeah, that's right. So we wanted to actually do this and see if it compiled, and it did compile by nature of using a custom maybe type. I'm going to refresh this page again, or maybe I should just switch to actual Twitch chat because this is being really unfortunate. The excuse me, my overlay was loading slowly as well, so I don't know what I should do about that. Anyway, it'll be fine. Okay, so we're gonna talk about apparently dependent pairs, and then I think that's pretty much it. Like dependent pairs, yeah, we're basically almost done. It's pretty wild to think about. Freeman, thank you for hosting with two chatters. Hello, chatters. How are you today? Okay, so we probably need all of this. Well, I guess we're calling it dependent. Then we gotta see what we need here. So we need constraint kinds, empty case, which I think I was using before. I'm gonna put this in order in the book so I don't miss anything. Flexible instances, GADTs. Put a space there. Instance SIGs. Okay. Multi-param type classes. I have that one. Param type classes. Rankin types. Oops. Yeah, I think I'm gonna switch to regular old Twitch dashboard. Okay, so we'll try this. Go from there. Sure. Okay. Chat's there. Neat. Okay. So, wonder if I can make this a little bigger. I can. I don't really care about that. All right, sorry. They came out with a new streaming dashboard for Twitch. It's actually a lot easier to see. Tells you how long you've been streaming, lets you edit the stream info. You can run ads, raid channels, clips, all kinds of things. So that's kind of cool. Anyway, scoped type variables is the next one. Oh, we used. We'll put that there. Standalone deriving. Okay. Template Haskell. Type applications. Type applications. Type families. Type in type. Undecidable instances. Okay, we're almost done, I promise. Supposedly that's it. And we need import data ASIN, import data constraint, import data kind. Oops. Type. Import data maybe app maybe data singletons dot prelude for data singletons. Cool. All right. Hey John, what's going on? The chat's a little smaller than I would like. It'd be nice if I could just hide this. I guess I can do this. Yeah, okay. Sorry, I'm trying something new on the other screen here, and it's kind of hard to deal with. How's your day? Not hard to deal with, it's just different. Asin. Stack. Build. Yeah, hopefully we'll be able to finish this today, and yeah, that's pretty exciting, actually. Wonderful. So I think what we're doing... It did not finish good. Unfortunate. What is that because of something I did or something you did? Oh, another cluster down. Right. That means you're awake. Got you. As soon as you said cluster, it reminded me from last week. So I'm sorry your cluster's down. It sounds like a very unfortunate cluster, actually. Okay. So sigma types, also known as dependent pairs, generalized arbitrarily deeply nested either types parameterized by a type. When viewed through the lens of the Curry-Howard isomorphism, they correspond to the existential quantifier sigma, but backwards. Yeah, I remember you saying that last time. It is unfortunate because I do lose a lot of Europeans, and I know that there's a lot of Haskell going on in Europe, so that's kind of unfortunate, but I mean, I have a job as well, so it is what it is. So sigma types are the pair of an existential singleton and a type indexed by that singleton. Consider the definition. Data sigma a type where sigma sing a yeah, I think so. Oh. Just a company that prefers to pay for downtime urgent stuff than fixing their core tech. Wonderful. Very useful. I would say that I'm generally having a good day. I spent some time thinking about convolutional neural nets today, and I thought I understood them. Turns out I didn't. But now I think I have a little bit more, a better idea of how they work and like why they're designed the way they're designed and these sorts of things. So during my day job, I'm trying to do machine learning. So, well, deep learning specifically. And it's hard. It's really hard. If you're not taking stuff off the shelf, it's very difficult. If you're just grabbing like an off the shelf model, it's super easy. But I can't use the one off the shelf. So anyway, so sigma takes a singleton or an existential type A of kind K and a data type FA. Notice that FA is parameterized on the existential type A. As a result, sigma F might be any number of possible FAs. Okay, interesting. So we have essentially I work for Random Cars 2. I don't know what that means. So I have audio clips of basically animals, and what we're trying to do is apply deep learning models to find these animals. And the problem is I can't tell the difference between certain animals. Like the oh, fair enough. I mean this also is very difficult Haskell. So I think if I showed you some more of the stuff we do on Thursday is probably a lot less confusing. This is defining a GADT and generalized abstract. I think that's right. Generalized abstract data type. So this sigma thing, we're gonna write stuff for in a little bit. So hopefully it doesn't make sense to me yet either. So I'm not really sure what it does. Okay, so yeah, I don't know what this does yet. So I think it will make more sense after we write some code, and that's usually how this book works. Is like you write some of this code, and then it starts to make some sense. Or it's not going to make sense to either of us, and we'll be done with the book anyway. And hopefully later I can come back and understand how this works. But oh yeah, I can explain. I mean this is basically yeah, deep learning for animal sounds. That's exactly what it is. Okay, so basically what's going on here, by the way, just so you know, is this basically is the input to the function. So it's like, give me this thing, singleton of A, and an FA, and I'll give you this. But what this is actually describing is just what sigma actually is. And we're going to use like a bunch of other functions to work with it. So here we have like this shape. We saw this shape before, right? That's the sigma shape, where R is the result that is sigma F, essentially. So if you give me a sigma, wait, that doesn't make any sense. Oh, we're going to get a function that turns one of these into an R. That's what we're doing. Jappy, how's it going? Yeah, this A, I guess, is supposed to be a type level existential, except apparently we have access to its singleton, right? So we're using this to access this, I think is the idea. I'm not 100% sure yet, so bear with me. It might make more sense when we get some more code ran. Maybe it won't. I mean, it's entirely possible it won't. Oh, typo. Right? It's not sigma R, it's sigma F. This F. Okay. So what are we doing? So C is taking one of these sigma types that has, wait, why is there two things here? I thought it was only supposed to have one thing. Okay, let's go look at some types here. No, wrong one. CD. So that's a sing. Is this an F of A? Ah. Yeah, okay. I wasn't expecting to be able to pull these two things out, but okay. So this is a sing A and then an FA. So C just takes those things. So if you just take CSF, you get an R. Okay, I'm fine with this. I'm still... Why can't I pull these things out? That's the only thing I don't understand. Maybe it's just because I haven't looked at Haskell in a little while. I thought this would be like an F. And I'd have to do like, I don't know, like some uncurrying or something. Okay, anyway, I'm gonna keep going. We'll see if it makes sense here or not. Sigma F. So we're gonna have an F. This... Sure. All right, so this sing... Hey, Typed Rat, how's it going? It has been a while. How are you? We definitely missed you on stream. You've helped us like immensely at the beginning. Also, the colorations in chat right now are great. The blue, purple, and I think that's pink. It might be on the purple side, but it's hard to tell for me. Oh, for sure. School is very busy, but glad to hear that you're doing well. All right, so this sing is a sing A, and we are giving it an FA so we can construct a sigma F. Sure, I'm fine with this. I hope also Lumi's here today because I did fix the issue I was having previously. Now I have to hit enter twice every once in a while, but that's a lot better than having to delete things. Okay. Yeah, I think I'm okay with this. So it says the singleton inside sigma can additionally be used to help cast a sigma F back into an FA, assuming the type inside is the same one being requested. This is done via sDecide to convince the type system such a cast is legal. All right. So I gotta put this down here. So for all K A K F K type. Dot. Sing oops. sDecide. Gosh, this is wild stuff. Yeah, so before, by the way, just for reference, if I would have typed this K, and hit enter, I would have gotten like the first thing here. And then I would have to like delete it and retype K and be fast. But now I can just hit enter twice and it'll pop down it'll get rid of the thing. Yeah, this is HIE. Yep, Haskell IDE engine. I have a video for setup on my YouTube if you need it. I have changed the config a little bit. So I'm using NeoVim and Haskell IDE engine. It's actually been really great, honestly. Yeah, singletons. I don't really know exactly what I'm doing here right now, but like I'm okay with being exposed to things that I don't fully understand and then coming back later. So that's kind of what I'm hoping for. Because this stuff seems pretty wild. What operating system are you on, Chappie? Because it was actually pretty easy on Linux. It just took a long time to compile. Yeah, you should be able to do it on Nix, NixOS. Like, who's the? There's another Haskell streamer that spent a lot of time with getting HIE and NixOS and all those things to play nicely. Freeman. I think he's got videos as well on how to do this stuff. I should probably write a blog post about this at some point. Although I think that it already exists, so it's probably a waste of time. Okay, so S. I'm gonna have to go back and look at this stuff again because I don't remember exactly what this is doing. But I think what we're doing is like basically just doing some I keep using the term theatrics to prove to the compiler that this stuff works. No blog post on Nix. That's probably true. I don't really know enough about Nix to help you, unfortunately. That's on my list of things to learn. But it was relatively easy to just compile from scratch. HIE, I mean. And I assume you can just get like a newish version of NeoVim on Nix pretty easily. To Galaxy Brain. I don't think you're a dummy. I don't think you're giving yourself enough credit there. Okay. So, what is going on here? I don't remember what this %tilde thing is. Okay, so %tilde takes basically two singletons and decides if they're the same, I think. So if we build a singleton of type A, it's decidable equality. Oh, and Jappy says, yeah, I understand at least the point of Nix now. I didn't earlier, but it's nice that you can just sort of get these configurations from the internet and just, you know, get everything working, but they have to exist. If they don't exist, that's not very helpful. So decidable equality. And I don't think that this is not a lens. It comes from, here, I can show you. It comes from decide. Oops. This. So yeah, so it takes basically two singletons and determines if they're equal using another operator. Propositional equality. So that's what it's doing. So type rat. Decide K means that you can affirmatively determine equality or inequality of two singletons of kind K. Yep. So maybe you could you give us a, do I have one? Hang on. I forget. What is the motivating factor for using this? Like the singletons? It's just to make dependent types work. Yes? Like it's a trick used to make dependent types work. Yeah, because if you have an isomorphism between types and values, you can do dependent type stuff without dependent arrows. What does dependent arrows mean? That has something to do with like category theory, probably. You don't need to have the ability to have a function from values to types. Okay. Yes, I think I understand that. Maybe the trick is that I don't know when I need that. I think that's kind of like the issue with some of these later chapters for me, is like I can't come up with great motivating cases for when I need this stuff. Yeah, you can't have a function in Haskell where the type varies based on the value. Yeah, it's okay. Yes. You want to do something different if at runtime based on values and not types. Okay. So it says here, by pattern matching on REFL at 1, GHC learns that A is, what's this T? It says A is equivalent to T, where T is the existential type inside of the sigma T. So this A, right? This A is the existential type inside sigma, I think. With this equality in hand, it's clearly safe to return the FT when asking for an FA. Is that clear? I don't know if that's clear or not, but anyway, it is apparently. So the dict function from our logging example can also be generalized into a type class capable of providing total constraints given a singleton. Okay. So we'll write this one. For all you've got for all t, sing t, ft, sigma f. Right. Because this A can be whatever. Yeah. Yeah. Right. Okay. So if I have this, which is like a sigma t, or well, yeah, a sigma tf or whatever. if I can prove that S is the same as A, so this could be T, right? This is the T that you're referring to. I think it should just have some. Well, yeah. But this is like some. Oh wait, no, that's apparently an A. Yes, yeah. That's what I meant. Sorry. That's what I meant. I didn't say it correctly, but that's what I was attempting to say. So if I can prove to the compiler that this and this are the same, then I can convert a sigma f to an f of a, but only if I can prove that this thing is true. Okay. I think I'm okay with that. I'm going to write a little note here. So think of S below as sing T. If sing T is equivalent to sing A at the type level, then f of A is the same as f of T. Right? Nice. Cool. Yep. Nice. Okay. That makes more sense. Yeah, that makes more sense. When it said T in here, I was a little thrown off. Like, did it? Let me see if it says something about the S. It does kind of say it, but in a slightly more roundabout way. It might be easier if it just said, like, think of S as a sing T. Maybe it would have been more clear. I don't know. Maybe not. Oh, here, let me put this on top. Okay, so I don't know what this is. The dict function from our logging example. I don't remember that, but okay. If I just had a better memory, I feel like a lot of this would be easier. AK C has kind type to constraint. How do I know that? By looking at this? Probably has something to do with this. But where does this even come from? Oh, from the constraints package. Okay. Maybe we should read this structured logging example before we do this? I'm not sure. It says it's a function from, does it define here? I'm a bit confused, but okay. Anyway, so C has kind type to constraint, and F has kind K to type. So we have A with kind K right here. We have A with kind K from the singleton. This chain of constraints can be traversed to get a constraint. Given a singleton, dict1 will provide the requested dictionary, and it will fail at compile time if the requested constraint isn't total over F. So it says a dict1 instance can be used to lift eq over sigma. Right? Oh, that's where the constraint comes from then. All right. So this is really wild stuff. Excuse me. Okay, so we're providing an eq instance for comparing two of these sigma things. Okay. If it's mind bending for you, then I don't feel bad for it being mind bending for me. I do hope that at some point I can revisit this stuff and it will make more sense. But there's definitely some more practical Haskell components that I need to understand first. So like I'm pretty excited for us to finish this book. Like I don't like leaving projects unfinished and then moving on to Book of Monads again to try and get a grasp on like monad transformers and free monads and these sorts of things, and then later reading more complicated code and trying to like understand what it does, because there's probably lots of code we could read to help us understand this. So percent SB of proved raffle case All right, so let's think about this. So we have some f of a and f of b parameterized by a singleton. If those singletons are the same, we compare them using this dict1 function. We didn't define dict1. Oh, it's just a class? What is this thing? I forget what this is. This has a name, I think. Is it that? Oops. Okay, so I got multi-parameter type class right, but why can I use this here? Is it that f of a's have instances defined of dict1, so I don't have to worry about that? Because I know the singletons are equal, I know that I can compare these two functors. Or they're not, I'm sorry, they're not necessarily functors, they're just f's. In the instance head. So even if I don't implement dict1, I'm just assuming that I have that. Oh, this is just creating a to implement it. We'll probably implement it here in a second, I suppose. I don't understand. Okay, you have to implement it to use that instance. Have to implement to use that instance, given an instance of dict1. I have an instance of eq. So this bit is building a constraint. It's building some kind of constraint. Gosh, this is so hard. For any f, I have a dict1 eq f instance 4. For any f, for any f, I have a dict1 eq f instance 4. I have an eq sigma f instance. Right. Okay. Okay. Now, yes, I see. I think. And is this stuff being derived for me? Or am I just saying that is this eq? Yeah, so I guess the question is this eq instance being derived for me somewhere? Or does it just have to exist? Oh, it's right here. No. Oh gosh, my head hurts already. Give me a second. I'm particularly confused. dict1cf lets you go from a singleton of type AK to a dictionary witness for the satisfiability of the constraint CFA. So C here is eq. at runtime, this thing is being proved. That's the point, right? That this happens at runtime. This happens at compile time. It's equivalent to saying for all A, eq FA. Okay. But don't I still need to know how to... I mean, I guess I'm saying that that's true. So somewhere, the eq instance for this FA has to be implemented for all A. How does it know? How does it, I guess that's the piece I don't understand. How does it know that for all A, I have an eq FA? Like, I guess I see that that's what's happening. But how does the compiler know where that's happening? Like, how does it pick this instance out? Exhibiting that I can do it. I don't understand what that means. So let me back up. So, like, somewhere there's an instance because the dict GADT contains the actual dictionary used both to carry the methods and to prove that it exists. So weird. Yeah, what you're saying is like right here. Interesting. There's something about this weird type, or seemingly weird type anyway. Of course, it's not all that weird. I'm sure the instances end up being weird, but, or, you know, the rest of this code is probably confusing as hell, but. Okay. I think that helps. It doesn't feel simple. Because okay. So like this thing here is bringing in, by pattern matching on dict, I'm bringing in equals equals for f's of A, essentially. Because I know that this is an f of A and this is an f of A. Because I know that these are equivalent. Got it. Okay. I get it. I get it. I think that I didn't understand that that is really happening here. By once you said that and I looked, I think it makes more sense. Okay, so by being able to pattern match on dict, the constraint that f of a and its implementation are brought in scope. Okay, so by being able to pattern match on dict, the constraint that eq fa, or it's not that, the constraint are available at compile time. We know FA and FB. Well, it's not the F's, it's really sigma. I probably shouldn't use this tilde here, huh? That's not really correct, because they're not... Well, maybe it is. Yeah, it's not... They're not equivalent. They have the same type. We know... Yeah, I know that the singletons are equal. Oh, I guess I don't know that FA is equal to FB. That's a good point. I only know that the singletons are the same. That's the whole point of this. I don't know anything like that. Yes. Yeah, I mean, this is enough information. I guess I should make this like an existential type, right? Like, yeah. So it's like eq ft, and both A and B are of type T. Okay. Let's write this out. Something like this, anyway. It's probably not perfect written this way, but... Oh, right. Actually, that's a good point. Then it is fine. Right. And then if the singletons are different, that implies that these F's, FA and B are different and therefore they cannot be compared. Nice. Thank you for that. It's really helpful. Maybe this next one will make more sense now. Well, oh, right. They have to be unequal. Good point. Because their types aren't the same. So they can't possibly be equal. That's a good way to put it. Okay. All right. Feeling maybe a little better about this now. Maybe. Oh, and then this demote thing gets in here and ruins everything. Show sigma f where show I'm guessing that's right. Sort of. Uh the this is technically correct, I believe, but you know, he's putting some more information in here, that's all. So instead of using show, yeah, instead of using show, they're just using a little more information. So like you'll see that it's just kind of superficial. It's not. Let me. Yeah. So this is what we get by writing this, and then how does it know? Well, okay, right. We can always do this. This is always allowed, right? From sigma. Or oh, that's from sing. Yeah, we can definitely always do that because it's a singleton. Okay. And I'm guessing that this demote k thing has something to do with this. Like the ability to write this, I mean. This whole line. That would be my guess. So, yeah, this comes from the combination of these two lines, and this comes from this. Well, this plus matching on dict would be my guess. We'll see if that makes sense here in a second. All right. I think it makes sense anyway. Oh, well, you might want to look at that. Leave that there. So this is exercise. I think it's the last exercise in the book, unfortunately. And we'll just work through the rest of this and be done. Pretty wild. Exercise 15.5-I. Ow. Funny bone. Provide an instance of ord for sigma by comparing the fs if the singletons are equal comparing the singletons at the term level otherwise. Okay, so I think that this ord piece is essentially going to look like this one. I'm just going to copy this. And then we'll fix the pieces that need to get fixed. So this is going to be ord. This is going to be ord. This is going to be, I think it's just compare. And then this is going to be ord. And this is going to be compare. And then if it's disproved, we have to compare the singletons. And I assume we can only do that via these two things. So I gotta stick these here. And this is gonna be ord. And then here we're going to say like compare from sing sa from sing sp, something like this. Sasp. I tend to pronounce things like that. Okay, so this would have been my guess. But we're having some error here, and I would like to see the whole error because it would be helpful. So stack build. Okay, so I need to prove that everything is also equal. I can't just prove yeah. So everything needs to be equal. Everything needs to be orderable. This gives me the ord instance for these. And this gives me the eq instance for these. Well, eq and ord. Sorry, that does. I think this is right. I'm wondering if all of this is necessary. So I'm going to start deleting stuff and seeing, well, that's not, that doesn't, no. Yep. So it needs all of that, I think. So that will cause the from sing to fail. If I comment this, what should happen is the compare should fail. if I comment this, I think this will fail. Well, the whole thing will fail, apparently. But there is a squiggly line here. I don't know what this first error is. Oh, yep. We need a superclass, so... Wow, this is really cool. I'm pretty happy with this. Makes sense anyway. Well, thanks to TypedRat, it makes sense. If you weren't here, I probably would have just been like blown away. But let's see if this is actually correct. I mean, it seems to compile, so in this case, it probably is correct. But I'd like to check the actual answer. So 15.5.1. So dict1 eq f. Oh, so the only thing that they're doing slightly different here is that you don't need this. Yeah, I need to put this here. I guess I don't need to save that. I don't need to define this f twice because I'm using let's see, it's gotta be coming from, I think, scoped type variables. It might be coming from higher than that. But these f's are the same. Just how the type system works. Okay. In this case. Well, it's not in this case, right? It knows the type of f, I see. You only have to provide it once. Oh, I didn't actually look at the the answer. I just looked at this part. So proved refl ord f, disproved compare. Yep, that's correct. Neat. Okay, we did it. That's that. See if it builds. Should build. Okay. So it says the last section of this, which is insane. I'm very surprised that we finished the book. Maybe I'll ask everyone or the folks that are here, what they want to do next. I notice there's another viewer. If you are welcome to saying hello, feel free to say hello. I like to talk to my viewers. So the next example and the last section is... Oh, I don't need to give it at all? That's interesting. I want to try that now. Why did I need asyn? What am I using in here that's from asyn? Guess there's an easy way to find out. Nothing, apparently. We also aren't using map maybe, I don't think. Oh, that can go away. We probably are using template Haskell, even though it's not super obvious to me. We're definitely using constraint, and we're definitely using this. It seems to think we're not using that, but we must, right? It's a start. I like that. You don't think we're using template Haskell? Okay. Oh, the strat. I see. Yeah, that's really small on my screen. Actually, we had this conversation that I'm very bad at or I'm very good at mixing up things like that. Okay, neat. So let's finish this book. All right. Oh, maybe they're including asins so that you can keep doing this. That's what they're doing. I get it. So this is meant to be continued in this file. So from I've been writing too much Python. Maybe. Yeah, maybe. So I think we're just going to continue at the bottom of this, and that's kind of what the point is. DT. So section 15.5.1 structured logging. Okay, so an example of what good are singletons considered as an, see, I did it again. Common use case from dynamically typed languages. Often, protocols will attempt ad hoc type safety by taking two parameters. The first being a string describing the type of the second. I've actually never done that. Is that a thing people do? That's kind of clever. Like in a dynamically typed language anyway. Anyway. This is a clear use for dependent types. The type of the second argument depends on the value of the first. In particular, it is a sigma type. Because once we know the type of the second parameter, the first is no longer of interest to us. To demonstrate the technique, consider the case of structured logging. When we have information we'd like to log, rather than emitting it as a string, we can instead log a data structure. The resulting log can then be interpreted as a string, or it can be mined for more structured data. For this example, we will assume we have two sorts of data we'd like to be able to log, strings and JSON. The approach can be generalized to add more types later, and the compiler's warnings will drive us. Cool. While an existentialized GADT approach might suffice, where we stuff proofs of each type class into the data type, it requires us to know all of our desired dictionaries in advance. Such an approach isn't particularly extensible, since it requires us to anticipate everything we might like to do with our log. Instead, we can pack this structured data into a sigma and use the dict1 class to retrieve dictionaries as we need them. We can begin by writing an enum describing which sort of data we want to log. Okay, so this is where we're going to use template Haskell, by the way. The data log type JSON message or text message driving keyboard show. Okay. An open data family log message of kind log type to type can then be defined. Log message is indexed by log type, meaning we can build a sigma around it. Log message as log type. Okay. For every inhabitant of log type, we add a data instance for log message, corresponding to the data we'd like to store in that case. Message for a JSON message equals JSON value Yeah, so this JSON and this value are both coming from asyn, if I remember correctly. So that's where that is. Data instance log message for text message equals text, which we didn't import, string deriving eq. So oh, maybe this needs to be tabbed out. Okay. Where is it getting text? Shouldn't that fail? I guess asyn must export text? A little confused. Where are those coming from? Oh, those are just data constructors. Oh, okay. These two things do come from, well, this comes from asyn, right? Value does. Yeah, confusingly named JSON, data constructors. Wonderful. Okay. I see. That is kind of confusing. I would have just expected them to come from those things, but anyway. Maybe I would have looked eventually. I mean, maybe I would have. It might become clear later. Okay. So now we're going to for a given constraint on log message, JSON message, and another constraint on log message, text message, so all right. So these constraints are going to be essentially eq, show, or ord. And this dict is going to be the dictionary for whatever constraint that we're considering, I guess. And these are just arbitrary names, which I assume we probably won't use later. Maybe we will. But I don't think it matters necessarily. Because we're probably going to do something like, I can't see it yet, but we're probably going to do something like infer these to get this, something like that. Infer might not be the right name there. Anyway. Okay, so now given a list of log messages, possibly generated via writer T, list of sigma log message or something, we can operate over them. For example, perhaps we want to just render them to text. So we're just assuming that these were given to us. But apparently we're just typing some like funny messages. Super green. Anyone know that reference? Willing. Oh. Let's see if anyone knows that reference. Oh, except I'm clearly missing a end list. I'm guessing that this is a overloaded strings problem. Yo. No, don't know that reference. I'll give. There's 3 viewers right now. I'll give them a few seconds. I guess it depends how old you are, but it's a very popular movie when I was a kid. I don't know how old you are compared to me. You were mentioning schools, but you know, you don't have to go to school necessarily when you're 20 or whatever. Anyway. Okay. Or, so this is just like a toy example. 23. Yeah, so it may be like, depending on your favorite genre of movies, it may be a little out of your, you know, time frame, if you will. Like, you may have been too young when it came out. That's the point. So if you didn't watch it, then you didn't watch it. Yeah, so here's that that trickery. Well, you know what movie it is? Or did you look it up? I didn't say what movie it was. You may have just Googled it, I suppose. It's from Fifth Element, is anyway the reference I'm considering. It's what's that guy's name? His name. I mean, his name in the movie is Ruby Rod, but I suppose he's not even pictured in any of these. I mean, there he is. Yeah, Ruby Rod. He says green a lot. Anyway, Chris Tucker. That's his name. There we go. Great movie. Okay, anyway, so the point is that by doing this, we're getting the dict that corresponds to either a JSON message or a text message via this machinery here, I'm guessing. I'm not really guessing. I feel like that's at least an educated guess, but okay, so let's try and run this. So stack REPL. Then we can import, oops, data foldable. We can say traverse underscore put strlen show logs. Neat. Um, my lip is starting to split. Sorry. I don't know if you ever had split lips before, but it's the worst. Okay, neat. We're gonna load this up here in a second, so let's do that. Okay, and then we can apparently do some more interesting stuff, so we'll see what this looks like. I have no idea where this is coming from. This is new. Upon re-entering via foreground, I'm getting that now, which is kind of fun. Oh, I see. You put the dot down here. Sing I A S decide K. That arrow. Sigma F. There's Matt Maybe. Um, okay. So I'm going to make an assumption that this will only cat for JSON messages. Is that what's supposed to happen? I'm not sure what's supposed to happen. Yeah, neat. Huh. That's kind of cool. So you could have like a bunch of different log types and then make queries against the particular types that you're interested in, I guess, or something like that. It's kind of cool. Um so yeah, we're done with this book. It was a pretty wild ride, I would say. So let's first close everything. See, yeah, that's back. So first things for that's not what I wanted to do. We are going to create a pull request for this because, you know, it's Hacktoberfest, so we shouldn't just like not use this as an opportunity to create a pull request. Usually we just push right to master, but you know, would be silly not to do that. It's a pretty big PR, so it's fine. So I think okay, let's finish this real quick. Kind of a boring procedure anyway, but we are officially done with this book. So again, this is the book we were working on. You can get the book if you want it via that link right there. So I would definitely recommend it for folks who want to go like super deep in Haskell, but I would not recommend it for folks who aren't particularly interested in that. Not obviously, or I said that completely wrong, but not surprisingly. There we go. There was some stuff towards the end that I definitely had a lot of trouble with. I remember, I think it was chapter 14. No, it's probably chapter 12, I think. Hang on, find it. No, it's chapter 11. Chapter 11, I feel like, was particularly hard as the extensible data chapter. But, you know, I still think it was a good book. I had fun with it. So yeah, this code's available online, and also I will post like the entire videos, or the entire video series on YouTube. So I think I just have that. It's not that. Yeah. So yeah, this is a super cool book, and it's definitely the only book available like this in Haskell for sure. So I remember reading, I don't remember where it was, like the motivation for buying the book basically said that, you know, he was tired of answering these questions over and over again on Stack Overflow and in Reddit, or what am I blanking on the other messaging platform that I never used, IRC. So he got tired of that, and then he wrote this book, and the book is really, really nice. So with that,